And actually, no, I'm not the main person behind Quantum Espresso. I'm one of the many people who develop Quantum Espresso. I just try to keep the activity going on in an order way. Okay, good morning to everybody, and thanks to the organizer for having invited me once again in Austin. I was very happy to accept to be here again, and so I hope that the fact that I have been invited again doesn't mean that nobody was too dissatisfied with my performance last time 2 years ago. Okay, I'm going to present in some detail, in some mathematical details, the density function perturbation theory. So maybe you will find the presentation a little bit technically heavy, but I'll try to explain what lies behind all those formulas that you will see. I'm used to teach to mathematicians. Okay, let's try again. So I'll just give a new attempt. Can you hear me? No? Yes? Yes, okay. Okay, so I'm going to present the strict minimum of density functional theory that will be useful for later discussion, and then the basics of density functional perturbation theory, and in particular the application to phonon calculation, which is a basis for electron-phonon physics, and also some details about the presence of electric field and the effect of a macroscopic electric field in phonons and the longitudinal transverse optic splitting. So density functional theory, guess you have already heard about a lot about it. Basically, you have to transform, it allows to transform a many-body problem into a set of equivalent problems for non-interacting electrons under an effective potential, as Feliciano has told you earlier. So you have the Kohn-Sham equations, in which the effective potential for electrons, for these fictitious non-interacting objects that are the Kohn-Sham orbitals, can be written as the external potential acting on electrons and plus a potential that is a functional of the charge density. It depends upon the charge density. And the charge density is written as a sum over the square of the Kohn-Sham orbitals. So, of course, the functional is something that has some mysterious properties. It's a mysterious object with strange properties, but there are reasonable approximations that are usable. What's happened? Louder? Oh, that will be difficult to keep this level of phonon emission for the entire hour. But anyway, I'll try hard. Okay, so there are sufficiently good approximations that are sufficiently simple for practical usage and practical to obtain very good results in a large number of cases, and there are extensions to the simple approximation that allow to deal with more difficult cases. So we may write down the electronic energy as a functional, also the charge density, and a functional in which you have the a kinetic term, non-interacting electrons kinetic term, an external interaction term, interaction with the external potential, the external potential, which will be the potential of the nuclei, and Hartree term, an electrostatic term, and finally all the rest under the form of an exchange correlation, what we call the exchange correlation energy. Then minimization of this energy leads to under the condition of orthogonality between the Kohn-Sham orbitals leads to the Kohn-Sham equations, and the potential appearing in Kohn-Sham equations is a Hartree potential, a classical electrostatic potential, basically, plus the exchange correlation potential. That's whose approximate form is of which some approximate forms can be easily found. Now, in practice, what happens? In practice, the way to solve Kohn-Sham equations, there are several ways in which you can solve Kohn-Sham equations in practice. One is the one I know better is based on plane waves and pseudo potential. So you have to expand the Kohn-Sham orbitals into a suitable plane basis set, which is a plane wave basis set in our case, and the expansion coefficients become our variables, the variables of the problem, the set of vectors. So a vector for each orbital, and the Kohn-Sham equations become a nonlinear matrix eigenvalue problem. So you have to solve self-consistently a matrix eigenvalue problem. There are a lot of advantages in this choice, and also disadvantages, actually a few of them, so which are quite well known. You have to introduce pseudo-potentials, so pseudo-potentials which represent the effect of the core, the core electrons that are chemically inert, plus the Coulomb potential of the nuclei on valence electrons. So you deal only with valence electrons here. Plane waves are quite simple to use, and there are a bunch of interesting numerical techniques that can be used with plane waves, in particular fast Fourier transform techniques that allow this method to be very efficient. On the other hand, you have a periodicity. Even if you don't have one, you have to invent one. And you need a lot of plane waves in spite of the presence of pseudopotential. So there is a trade-off between this approach, between the simplicity of plane waves and the number of plane waves that you need in practice. Now, okay, this for the basis calculations for the self-consistent solution of a given system with given nuclear positions. So what happens if you have some change in the potential, in the external potential that is present in the DFT equations? So the potential that acts on electrons, which in our particular case, with the plane wave pseudopotential approach, will be a pseudopotential, which in general would be also non-local, a non-local object. In general, is a non-local object. So what happens if we add some external potential term? depending upon a parameter. Let's call the parameter lambda. Lambda equals 0 is the ground state. Finite lambda is a small finite lambda is a perturbed case. So we can write the potential acting on electrons as a function of lambda and expand it around lambda equals 0. And this gives this expansion. So the point is now, how can I write the equivalent expansion terms for the charge density and for the energy? Now, if we stick to first order, the first order derivative of the potential of the energy with respect to this external potential, the external parameter that in general will be a nuclear position, typically will be a nuclear position or an electric field in practice. So if the first order derivative is quite simple to compute because there is the equivalent of the Hellman-Feynman theorem that holds in the FT, thanks to the variational character of the energy function. So the energy function is minimized by the ground state charge density, which means that if you write the first order perturbation, the first order derivative of the energy, you will have a term in which you have just basically the matrix element of the perturbation, plus a term that should have a dependency upon the charge density, the variation of the charge density, the derivative of the charge density that vanishes because the energy is variational. It's minimized by the charge density, the ground state charge density. Okay, so that's simple. And also one can show quite simply that in general, the 2n+1 order derivatives of the charge of the total of the energy, the DFT energies, depend only upon the order n in the change of in the derivative of the charge density or of Kohn-Sham orbitals, the so-called 2n+1 theorem, which means that with a linear response of the charge density, you can compute the derivative, the energy derivative, up to third order. Now, second order derivatives are less obvious. Of course, this time we cannot avoid to compute these quantities, derivative of the charge density with respect to the perturbation. So this first order, the linear response, the first order response to perturbation. And this can be generalized if you have more than one perturbation, more than one of those lambda parameters can be generalized to mixed derivatives, and it gives you this expression here, which, funnily enough, is clearly independent upon the order of derivatives on the left-hand side. This term here is also clearly independent upon the order of derivatives. This term here must also be independent upon the order of derivatives, even if it is not at all obvious from its aspect. Doesn't look really, doesn't look that the order of derivatives can be exchanged, but it can. And this is something that actually is used in practical calculations. Now, in order to proceed, we need this quantity, the derivative of charge density, with respect to the external perturbation. Now, this can be found in two ways. Basically, one can go back to this expression. So write explicitly this second derivative of the energy as a function of this. So you expand the potential, you expand the charge density up to first order. you drop it here, you get the second order derivative as a function of the derivative, the first order derivative of the charge density, second order derivative of the energy as a function of the first order derivative of the charge density. You minimize this functional because it has to be minimum, and you find the value of the derivative of the charge density, the linear response. You find it this way. Alternatively, you can use a self-consistent procedure and perturbation theory, which is a more traditional way to achieve the same goal, but it's absolutely equivalent. So what is the linear response of the charge density? It can be written, here I'm assuming a non-magnetic insulator. What is written here is incorrect. It's a non-magnetic insulator. So it's a sum of, it's a product of Kohn-Sham orbitals times the linear response, basically, summed over all Kohn-Sham orbitals. And the derivative of the Kohn-Sham potential contains a bare term, the term that comes from the external potential, or pseudo potential in general, plus a term coming from the Hart potential, and a term coming from the exchange correlation potential, which is written here is in a formal way via the functional derivative of the exchange correlation potential times the linear response of the charge density. Now, we still don't know the linear response of the Kohn-Sham orbitals, but we can obtain it from the linear response of the Kohn-Sham orbital, of the Kohn-Sham potential, using perturbation theory. Now, in perturbation theory, here you expect to have it looks funny written in this way, but it's actually the same as a perturbation sum, in which you have a sum over unoccupied virtual state. So PC here is a projector over the empty state manifold. Something that should be clear at this stage is that we are dealing with properties that are ground state properties, so well within the reach of density functional theory, which is in principle a ground state property. Even if there is this sum over unoccupied states, over virtual states. It's a mathematical trick, but the quantities we are computing here are ground state properties. Now, so this is the perturbing potential screened by the linear response itself. This is 1 over epsilon V balance minus epsilon C summed over epsilon C. It's written in this way because it's the same actually. It's actually absolutely the same. The projector of the empty state manifold is used because if you have a manifold of occupied state and you perturb this manifold, you have to add something outside this manifold in order to change the charge density. Otherwise, you just rotate, just perform a rotation, a unitary rotation in the space of occupied manifold, and nothing happens. The charge density remains the same. So it has to come from, the contribution has to come from the unoccupied orbitals. Now, this is a sum of, so apparently it's a sum of unoccupied states, which is very inconvenient to have in a numerical framework for various reasons. It's something we don't want to deal with unoccupied states. But actually, the way not to deal with occupied states is known since many years in atomic physics. It's called the Sternheimer equation. you just solve, instead of performing the sum here, you just solve a linear, you transform this into a linear problem. So you write this quantity here, which is the Green functions basically, times the quantity I want to compute equals something I know. This is a linear equation. It's a linear problem that can be solved as a linear system. So there are techniques to solve this linear system that are very powerful. If instead you use the other approach, that is to expand the functional of the energy at the second order and minimize it, you get exactly the same equation, but written in a different way. Instead of getting many linear equations here, many linear systems to be solved, one per occupied state, and the connection between the many linear system that is happens via the charge density. This depends upon the linear response of the charge density, which depends upon the solutions. What you find is a big linear system for all of those objects all together. So it's the same written in a different way, or seen in a different way. Now, those set of equations, those three equations together form a define a self-consistent procedure that can be solved iteratively, which is quite similar actually, but simpler in principle than the solution of the Kohn-Sham equation. And more or less it costs something in the same order of magnitude as a Kohn-Sham, as the solution of Kohn-Sham equations for the ground state. Now, as I've mentioned before, the projector of our conduction state, which is needed for to ensure numerical stability, so to get rid of contributions that are not there, are not supposed to be there, can be written as 1 minus the projection of the valence manifold. So actually, you don't need the conduction manifold ever in this procedure. Of course, you have this quantity here, but it's not too difficult, at least for this relatively simple LDA or GGA. This term here, this functional derivative, is something that can be written down explicitly or computed numerically in a relatively straightforward way, so it's not a big problem. In addition, this machinery works nicely, has no problem with non-local pseudopotentials. With ultra-soft pseudopotential, things are a little bit less simple because there are more terms that appear here. I'm not going into detail. There are some terms that appear both here in this solution and in the energy, in this second derivative of energy. But anyway, for non-conserving, non-local pseudopotential, the procedure is quite straightforward. And the important point that Feliciano already mentioned is also that it works for any monochromatic perturbation. So for a monochromatic perturbation means a perturbation with a finite wave vector, a single but finite wave vector, Q. In the following, Q will be the wave vector for perturbations, while K will refer to the block vectors of orbitals. So this is because working with linear response, the response has the same perturbation, the same monochromaticity of of the perturbation. So there is no need, finally, there is no need ever to use supercells, even for perturbation that have non-zero periodicity, non-zero wave vector. So that's the basic procedure to get the linear response from which you can get second-order derivatives of the energy. Also third-order, but it's more complex. Now, how can we use that in practice for Phonon calculation, for solving the problem of phonons in crystal? Well, first of all, let's consider the case of finite system. It's a textbook problem. You may expand the energy up to second order in displacement, in nuclear displacement, and by diagonalizing, so your second order derivatives of the energy are called force constants, and by diagonalizing this matrix of force constants with the constraint of with an additional, it's a generalized diagonalization, so there are masses here, the mass matrix here. So you have to diagonalize the force constant matrix divided by the square root of the masses to find normal modes. Then you find, what you find is a set of harmonic oscillator and of frequencies, and these harmonic oscillators are basically independent. So that's the harmonic in the harmonic approximation. So if you stick to second order expansion of the energy with respect to nuclear positions. Now, in crystals, what happens in crystals? In crystals, your Kohn-Sham orbitals are classified with block vector K. You have a band index I. That's textbook solid state physics. You have a periodicity defined via a unit cell that is periodically repeated, and your atomic positions are identified by their position in a unit cell plus the position of the unit cell. So you write here the atomic positions as position in the cell plus position of the cell. Now, also phonons are classified by block vector. And they have a block vector and a mode index. And so one has to solve an equation that depends upon specific block vector of the phonon, in which this matrix here, this force constant matrix at finite at a given wave vector, is the Fourier transform of the force constant matrix in real space. So this force constant matrix depends upon the distance between the two ions that are moved, that are perturbed together. Or if you prefer, you perturb one atom and you look at a force on another atom. That's a force constant matrix. This is in real space. For phonons, if you want to have phonons at a given wave vector, then you have to consider the Fourier transform of real space force constants. Now, you cannot directly compute those quantities here in a crystal. You cannot because you have no way to displace, to apply perturbation to a single atom of the entire crystal. You can deal with monochromatic perturbations only, basically, or whatever wave vector you want, but you have to stick to monochromatic perturbations. In fact, if one considers monochromatic perturbation, so if one writes the position of an atom as the unperturbed position plus the perturbation, then one can compute the second order derivative of the energy with respect to this quantity in reciprocal space and directly find the Fourier transform of the force constant in reciprocal space. So those quantities here, force constants in reciprocal space, are directly computed, can be directly computed as a response by a response to monochromatic perturbation. Now, this means that you have in practice to compute how many linear response calculations. Well, if you have n atoms in a unit cell, you need 3 times n atoms, number of atoms, linear response, in order to get the entire matrix of force constants. But you don't need any supercell. Also, something that has to be mentioned here is that given that the phonon frequencies are typically much smaller than the electronic frequencies, the frequencies that are relevant for the electronic motion, one can apply the adiabatic approximation. One can, in the spirit of adiabatic approximation, one can consider the linear response, the static linear response, even if phonons are in principle dynamical quantities, they are vibrations, so they have a dynamical aspect, but one can actually use the static response, which means that here is all you need. You don't need to add any phonon frequency in the response, as one should do for really dynamical, if one would consider the dynamical linear response, not the static one. Now, once you have the possibility to compute the force constant matrix in reciprocal space on whatever grid, on whatever wave vector you want, the convenient way to proceed is to get force constant, interatomic force constant in real space by inverse Fourier transform of the force constant matrix in reciprocal space. So what is done is that one computes on a discrete grid of wave vectors, Q, the discrete grid that spans the Brillouin zone. One computes and performs many calculations of the force constant in reciprocal space. Then, by Fourier transforming force constant in reciprocal space to real space, what one gets, well, this is a grid that is discrete and periodic. So you Fourier transform, you make a discrete Fourier transform, and you get a grid that is discrete and periodic in real space. The periodicity is dictated by the grid in reciprocal space. So the denser this grid, the larger the periodicity. If you work with Q equals 0 only, the periodicity is the same as that of the crystal. But with a denser grid, you get super periodicity in real space. And since real space force constant tend to be short range, tend to decay quite quickly, with a relatively small number of calculation in reciprocal space, you get a sufficiently large supercell in real space, and it is sufficient to describe your interaction in real space between your force constant in real space. So this works quite nicely. There are some technical tricks that are may make calculation faster. In particular, if you have symmetry, you better exploit symmetry. So the calculation and the computation are done only on a subset of the needed wave vectors, the reciprocal space wave vectors, Q. And then using symmetry, one generates what is needed, the reciprocal space force constant on the entire grid covering the Brillouin zone. Now, this works very nicely for at least for cases in which reciprocal real space force constant are short range, actually. For instance, silicon and germanium, simple semiconductors, all cases in which this is true, and so the calculation can be done in a straightforward way, and that's the end, more or less the end of the story. We have a force constant in real space, and we can generate phonons for whatever wave vector we like. Things, unfortunately, are not that simple in most cases, actually. So silicon and germanium are easy cases. Cases that are less easy are those in which you may have that in the limit of zero wave vector, there is a macroscopic electric field that appears. Now, for silicon and germanium, which are non-polar and which have high symmetry, very high symmetry, there is no possibility to have the macroscopic electric fields appearing generated by a phonon in the limit, in the Q equals 0 limit, in the long wavelength limit. Now, what is the problem? So what happens in practice? It happens that those phonons here split. So those frequencies, those three frequencies, in this case, there are three frequencies here. There are 2 atoms per unit cell, so there are 6 phonon modes. 3 are here, the acoustic ones and the optical one. So the acoustic ones are modes in which atoms move in phase, and optical are modes in which atoms move against each other. Now, the problem is, so in principle, many materials actually, in the limit of 0 wave vector, you have a macroscopic electric field that appear. So what is the problem? The problem is that macroscopic electric field is an object that is incompatible with periodic boundary conditions. So it breaks periodicity. So it has to be treated separately from the rest of variables. So it's a sort of additional variables that one has to add manually to the system. How is it done? Well, this was done many years ago, and it's explained in a lot in detail in a well-known book, the Born and Wang, Dynamical Properties of Matters, or something like that. I guess it's a book that everybody cites and very few people actually read. It's anyway an old book, and the results are well established by now. So let me try to give an explanation of what happens. So you may, in the limit, in the 0 wave vector limit, write a sort of phenomenological expression of the energy as a function of nuclear displacement, so the displacement from the equilibrium positions, U, and macroscopic electric field. So you add the macroscopic electric field to the system, and you write a quadratic term in the displacement, atomic displacement, which has the form that we know. So force constant matrix times two times the atomic positions squared. Then we have another term, which is an electrostatic term. This electrostatic term can be described as the square of the electric field. And since there is, we are dealing with electrostatic energy in the matter, there is the electric constant that appears here in the middle. This actually, in general, is a tensor. And then there is a term that couples the two, the electric field and displacement. There is a quadratic term in which the two variables are different. So they are the term that couples the nuclear positions and displacement and the electric field. This term here, this Z star, these are called the Born effective charges. Now, with some electrostatic, one can find under which condition an atomic displacement, a phonon, generates a macroscopic electric field and what happens. So by considering the Q equals 0 limit of an electric field, one immediately finds that the vector product of the wave vector times the polarization, the electric field polarization has to be 0, which means that the electric field can only be longitudinal. Then since the screened electric field, so the electric field plus the polarization induced by electrons, the electronic polarization and the nuclear polarization, since this has to be orthogonal to Q as well, one finds that the electric field, the longitudinal electric field, that in fact appears only for longitudinal optic phonons, can be written in this way. And then, in fact, it's longitudinal here. And by putting it back, putting this value back here, one finds an effective force constant that takes into account for nuclear positions only, that takes into account the existence of those macroscopic electric fields in the Q equals 0 limit that has this form. So this form is, this term, additional term is non-analytic, which means that it depends upon the way we go to zero wave vector. So whether we go with displacement, phonon displacement in the direction of the wave vector or orthogonal. But notice that the Q equals 0 value, the Q equals 0 phonons, or longitudinal optic and transverse optic phonons, are not distinguishable at Q equals 0, of course, because Q equals 0, well, the difference between longitudinal and transverse is non-existent at Q equals 0. So it's the way we go towards 0 that makes the difference. The way to go to, we go to the limit, we reach the limit, Q equals 0 limit, that makes the difference. So this non-analytic term can be added to the force constant matrix, and in particular, gives us a possibility, the way to compute interatomic force constant in the presence of LO-TO splitting, which, by the way, except for a very few crystals, is always there. It's most of the time there, so you can just ignore. It works that way. You compute the the force constant in real space on a grid. At q equals 0, you have the non-analytic term, but you can just remove the non-analytic term, ignore it at q equals 0, and leave it at finite q, because you will get a discontinuity, a non-analyticity that will make the Fourier transform fail, because for a good reason, that is the real space force constant are no longer short range due to the presence of macroscopic electric field. So what is done, you have to simply subtract out a function of q that has the correct limit at q equals 0 and has a reasonable form at finite q. You subtract out, and then once you subtract out this non-analytic term, then you have what is left is short range, so you can perform the Fourier transform to real space and get short range real space force constant. And then when you need the force constant at the different wave vector, then you have to re-add the same quantity that you had subtracted out when performing the Fourier transform. Now, how can these quantities that appear here, effective charges and the electric tensor, this, by the way, is the electric tensor for electrons only, so the electronic only contribution to the electric tensor. Well, these are second order derivatives of the energy, in which you have to, so the second order derivative to 2 times electric fields, or 1 time electric field and 1 time nuclear positions. So the effective charge is actually the polarization induced by lattice distortion, or the force induced by the presence of an electric field. So what we need is, we need to figure out what is the response to an electric field. Now, again, there is a usual problem that the electric field has a bad behavior, has an ill-defined behavior, because the potential of an electric field is basically the product of minus the electric field times the position operator, which is not periodic. But this can be it's something that can be dealt with relatively simply, at least at linear order for linear response, in the linear response case, because what we need, what is ill-defined in the macroscopic electric field, in the macroscopic, in the potential of an electric field, what is ill-defined are matrix elements, diagonal matrix element of the potential. The diagonal matrix element of the potential is not well defined. But what we actually implicitly need here are only matrix elements between occupied and empty states. Implicitly, this is all we need. So those objects here, those matrix elements, can be transformed into a well-behaved matrix element using this trick. This is an identity. And once we have this, we can obtain the potential of the electric field potential, so the position operator times a wave function, an all-occupied wave function, we can write it down by solving an electric linear term, this linear equation, linear system, which comes from here. It's the same as written here. By taking this 1 over epsilon c minus epsilon v and rewriting it as under the form of green function and solving the linear system. Now, so now the problem is displaced to computing the commutator of the position operator with the Consham Hamiltonian, but this is something that is well defined and rather straightforward to compute. It's basically the operator P apart from factors plus the commutator of the non-local part of the pseudopotential in case the pseudopotential is non-local. But this is also something that can be computed without too much difficulty. And again, one uses, every time one encounters the operator position times wave function, Consham orbital, then one resorts to this trick. And finally, one finds that by computing the linear response to an electric field, that is three electric field, that's three direction, one can compute the effective charges, and in a similar way the tensor, the dielectric tensor, the electronic part of the dielectric tensor, can be computed in a quite straightforward way. There are some technicalities, but let's skip all this stuff. So finally, one has to compute in the generic case, one needs linear response to all perturbations of all atomic displacement, 3 times number of atoms in the cell calculations, each one costing more or less the same as a cell-consistent calculation, plus the response, the linear response to 3 components of the electric field. This is all we need. Just to mention something that I discovered in this school. There is also another term that may introduce a non-analyticity in the force constant. It's described in this paper written here. It's a quadrupolar term that also has a sort of non-analyticity that would be good to subtract out and to re-add, subtract out before the Fourier transform and re-add later if you need it. It's less important than the LOTO splitting, but still it's something that should be taken into account. So finally, one finds that phonons in materials that have LOTO splitting, like gallium arsenide. In gallium arsenide, you don't have the symmetry operation that sends an atom into another, and so one atom over one sublattice into the other sublattice. So you have you may have longitudinal transverse optic splitting. Okay, there's a bunch of this is not the last version. Okay, it doesn't matter. There's a bunch of things that you can compute directly with after Phonon calculation using density function perturbation theory. So you can compute directly infrared intensities for zero wave vector phonons. They are related to the polarization induced by a phonon, so they are can be computed from the phonon displacement pattern and the effective charges, Born effective charges, Z star. Most important for this school, electron-phonon interaction coefficients, which are a basic basic quantity for, just as Feliciano has told you before, which are the basic ingredient for all kind of calculations on electron-phonon related properties and phenomena. And the basic ingredient, the very basic ingredient, are matrix elements of the potential, of the linear response of the potential between orbitals, Kohn-Sham orbitals. So this is a perturbation of wave vector or monochromatic wave vector Q. This is a block state of wave vector K and K plus Q. So these are non-zero. And this can be directly computed with because this quantity here is available at the end of the calculation. Once you have computed the phonons, well, you can compute this for each displacement, each phonon displacement, and then sum over the phonon displacement, the phonon displacement pattern, and then you get those electron-phonon interaction coefficients. Something that is maybe worth also to mention is that the machinery of density function perturbation theory can be recycled also in other cases. In particular, it can be reused in many kind of many-body perturbation theory calculations. So in GW, for instance, you may use the idea of avoiding the summation of conduction state by performing it's called Sternheimer equation, so solving linear systems instead of performing perturbation sums. This is something that can be useful and used actually in some codes, at least for GW, for instance. And also you can extend, this machinery can be extended to time-dependent phenomena, to time-dependent density function perturbation theory. But there are other things many other things that can be computed directly with the density function perturbation theory, and many others that can be deduced, can use the results from density function perturbation theory as basic ingredients. A few references. Well, actually, these are not the. I have updated this list of references, so I removed this one. It's not interesting for you, I guess, and instead I've added a reference that two references that deal with something that I haven't mentioned here. That is how acoustic sum rule can be used to improve, to impose known properties to phonons. In particular to the matrix elements of force constants. The force constants have to obey some acoustics, some rules, some rules. And the other paper is about how to deal with two-dimensional cases, which are very field that has big interest right now. Okay, I think I can stop here. Well, electron-phonon coefficients without computing directly the phonon. Well, no, I don't think it is possible. But you you can compute those matrix elements using different approaches. For instance, with frozen phonon, so you distort, you make a distortion of an explicit distortion. You freeze a phonon with a small displacement into a system, and you compute the quantity you need by finite differences, finite numerical differences, so-called frozen phonon approach. It's sometimes it's the only way to do the calculation when linear response calculations are too complex. In general, it's I don't think it's convenient in all other cases. No, it's sorry, I can't. Yes. So you're asking whether this quantity, this derivative of the wave functions here, the Kohn-Sham orbital with respect to lambda, whether they are orthogonal. Well, for sure they have to be orthogonal to the valence manifold. By construction, they well not by construction. So it's imposed explicitly just in case, but they have to all be orthogonal to the valence manifold. Yes. They have to. Yes, they have to. Yes, it has to the derivative. Yes, if you integrate the derivative of the charge density over some parameters, if you integrate it is 0, and this must be also 0. So it has to be 0. Yes. Well, it's imposed. Now I don't remember exactly how, but it's imposed the orthogonality. Yes, you have to ensure that those perturbations, those perturbed Kohn-Sham orbitals are orthogonal. Yeah, they are orthogonal to each other. Yeah, it has to be imposed. Yes.
Okay, one more question.
Which pseudo potential are better for solid state calculation? Sorry. Well, this is not necessarily related to the FPT. It depends upon the kind of system you have in mind. If you, if you have some kinds of atoms that have a very, very hard pseudo potential, like 3D materials or rare earths, then necessarily you have to resort to ultrasoft or PAW pseudopotentials. Otherwise, norm conserving, especially modern norm conserving pseudopotentials, tend to work well. Does it answer your question? I'm not sure.
So Paolo, for the audience here, Paolo will be around, so I think we will move on and we'll have a few questions from the Zoom audience.
So from Zoom, what is the origin of the electric field that you showed? And is this origin numerical or is it physical?
No, it's physical. It's physical. So this theory derives from something that is easily observed in solid-state physics. So there is a macroscopic electric field that arises in the zero limit, zero wave vector limit. And the origin is that in principle, if you look at electrostatic equations here, if you have if you consider the case of simple semiconductors, so two atoms oscillating one against each other, again oscillating against each other, you have three phonon polarizations that are possible. And the one that is directed along the Q equal, the defined but tending to zero wave vector gives rise to a macroscopic electric field. What is difficult to grab is that at Q equals zero, there is apparently no difference between the longitudinal optic and transverse optic modes. They look the same. I mean, even in those simple semiconductors, well, they have the three different, the three polarization, but there is nothing special about one polarization with respect to the other. So it's just the way you go towards zero wave vector that makes the difference. This is something that's a little bit hard to grab. Also, one should consider that this theory actually holds only in the electrostatic limit. So if one takes into account what happens really in with electrodynamics and not electrostatics, things are a little bit different. But anyway, the phenomenology is still there. This phenomenology is still there.
One more quick question.
Yes?
The question, but in the interest of time, I will ask one last one. So in the FPT, somebody is asking about how the perturbation affected by the periodic boundary condition.
Well, the perturbation, perturbation is not. I mean, the system has periodic boundary conditions. A perturbation that breaks periodic boundary conditions, like a macroscopic electric field, of course, has to be dealt with separately. But perturbations like phonons, so displacement from the equilibrium of atoms, are as long as they are monochromatic, they don't break periodic boundary conditions, as long as the wave vector is allowed by periodic boundary conditions. But that's a non-issue.
Okay, so thank you. Let's thank Paolo one more time. We have three announcements to make. So first, we are going to have a coffee.